Bringing a loaded cargo truck to a halt requires grinding friction, pressing brake pads against a spinning wheel. Yet this high-speed train achieves the same silent deceleration without any physical parts clamping down on the axle. We see a similar gap between expectation and reality in the kitchen. To boil water, we usually look for the blue flame of a gas stove. On an induction hob, that same pot of water reaches a boil while sitting on a glass surface that is cool to the touch. In classical mechanics, stopping a moving object typically requires physical friction, and cooking requires an external heat source. These technologies operate differently, generating force and heat across a gap of empty space. Both of these applications are powered by an electromagnetic phenomenon called eddy currents. By manipulating invisible magnetic fields, engineers have replaced mechanical wear and open flames with a system based entirely on electromagnetic resistance. This diagram shows a magnetic field intersecting a flat, electrically conducted metal surface. If the field is stable and the metal is stationary, nothing happens. But the moment that magnetic field begins to fluctuate, a reaction occurs. This fluctuating field induces an electrical current inside the metal. Instead of following a straight path, electricity-driven swirling loops, eddy currents, form directly within the material. This triggers Lenz's law. Nature resists magnetic change. As these swirling currents appear, they generate their own magnetic field, pushing back against the original magnetic change and exerting a physical force. While the effects were observed earlier, it was the French physicist Leon Foucault who properly identified and described these internal swirls in 1855. He was building on a phenomenon discovered by François Arago in 1824. Arago found that if he spun a magnet over a non-magnetic copper disc, the disc would begin to rotate along with the magnet, even though they weren't touching. This laboratory experiment demonstrated that magnetic fields can exert physical force on conductive metals across empty space. If the magnet moves, the resulting eddy currents create enough magnetic resistance to drag the metal along with it. Modern industry has taken this magnetic opposition out of the lab and used it to build auxiliary brakes for heavy-duty vehicles and high-speed trains. In this system, powerful electromagnets are placed near a metallic drum on the vehicle's axle. When activated, the rotating drum passes through a fluctuating magnetic field, inducing wide opposing swirls of electricity that create enough magnetic resistance to slow the rotation without physical contact. This raises a question of energy conservation. A 1,000-ton train has a high amount of kinetic energy. If physical brake pads aren't absorbing that energy through friction, it must be converted into another form. That energy is converted into heat through a process called Joule heating. Because the metal drum has electrical resistance, the energy from those large-scale swirling currents turns directly into thermal energy. While transport engineers work to dissipate this heat, the designers of induction hobs use it as their primary heating mechanism. Coils beneath the glass surface pulse a high-frequency magnetic field into the pot above. This generates concentrated eddy currents specifically in the walls of the pan. The pan's electrical resistance converts those currents into heat, warming the metal while the glass remains cool. By managing electromagnetic resistance, engineers have split the phenomenon into two specific tools: frictionless force for stopping trains and targeted heat for cooking. Although useful for stoves and brakes, this phenomenon is a significant liability for devices designed to transfer electricity, such as power grid transformers. Inside a transformer, changing magnetic fields create substantial, unwanted eddy currents in the metal core. This causes a persistent energy loss, where electrical power is accidentally converted into heat and wasted. To prevent this loss, engineers divide the transformer's core into thin, insulated layers called laminated sheets. These slices stop large eddy currents from forming. Instead, electricity is trapped in tiny loops within each layer, generating far less heat and preserving efficiency. This physical layering fails at very high frequencies, where heat generation increases. In these cases, engineers use ferrite, a material that is magnetic but has high electrical resistance, to stop eddy currents from forming in the first place. This same Leon Foucault is famous for his pendulum, which allows us to see the rotation of the Earth. But his work on eddy currents shows us another invisible, continuous physical law. Changing magnetic fields will always create opposing currents. Whether we use them to stop a train, cook a meal, or try to suppress them in the power grid, understanding these swirls is a requirement for modern technology.